the equation given for col A. Let x equal 2743, x2 equals 6858, x3 equal 9637. So we need to construct the orthogonal basis for col A first by using the Gram-Schmidt. We always start by setting our first vector v1 equal to the first basic vector, so v1 is equal to 2743. Now we get the step 2 where we take our second vector x2 and subtract x2 dot v1 divided by v1 dot v1 times v1. Now substitute vector x2. Well, x2 dot v1 will be 6 times 2 plus 8 times 7 plus 5 times 4 plus 8 times 3, and simplify, we will get 112. Then v1 dot v1 will be 2 times 2 plus 7 times 7 plus 4 times 4 and 3 times 3. We will get 78. Then substitute vector v1. Simplifying these expressions, we will get v2 equals 3.1282, negative 2.05813, negative 0.7436, 3.6923. Finally, for the third vector v3, we will take x3 minus x3 dot v1 over v1 dot v1 times v1 minus x3 dot v2 over v2 dot v2 times v2. Time to substitute all the vector based on the formula. Now simplify. x3 dot v1 is 9 times 2 plus 6 times 7 plus 3 times 4 plus 7 times 3, which is 93. Then v1 dot v1 is 2 times 2 plus 7 times 7 plus 4 times 4 and plus 3 times 3, which is 78. For x3 dot v2 is 9 times 3.1282 plus 6 times negative 2.0513 plus 3 times negative 0.7436 plus 7 times 3.6923, which equals 39.4613. For v2 dot v2 is 3.1282 times 3.1282 plus negative 2.0513 plus negative times negative 2.0513 plus negative 0.7436 times negative 0.7436 plus 3.6923 times 3.6923, which equals 28.1795. So we simplifying these expressions, we will get v3 equals 2.2348, 0.5264, negative 0.7279, negative 1.7475. So the orthogonal basis for col A is 2743, 3.1282, negative 2.0 513, negative 0.7436, 3.6923, 2.2348, 0.5264, negative 0.7279, negative 1.7475. That's all for me. Thank you.
After we find the orthogonal basis for the code 8, so now we are using the Gram-Schmidt to determine the orthonormal basis for the code 8. So now I want to let my Q equals to the orthonormal basis for the code 8. So my Q will be equal to the set the notation, the vector 1 divided by the non-vector 1, vector 2 divided by the non-vector 2, and vector 3 divided by the non-vector 3. So I just substitute the vector 1, vector 2, and vector 3 that I found in the orthogonal basis for code A. So I can find the vector 1 divided by the non-vector 1, which is equal to 0.2265, 0.7926, 0.4529, and 0.3397. And then for my vector 2 divided by the non-vector 2 will be equal to the 0.5893, negative 0.3864, negative 0.1401, and 0.6956. And then for my vector 3 divided by the non-vector 3 will be equal to 0.7510, 0.1769, negative 0.2446, and negative 0.5872. Then my orthonormal basis Q will be found in the diagram, which is the 4 times 3 matrix. Okay. Now I want to find the QR equals to 8. Since I want to find the R, so I want to multiply the inverse of Q to the left hand side and the right hand side. So I will change the inverse of Q to the Q transpose. So my R will be equal to the Q transpose multiplied with the matrix A. So I substitute the value inside so I can find the matrix as shown below. So this is a 3 by 3 matrix. AX equals to B. If the A equals to QR, then I substitute the QR inside. So QRX will be equals to B. Multiply the inverse of Q for the left hand side and right hand side to find the RX equals to Q transpose B. Okay, you need to change the inverse of Q to be the Q transpose. After that, multiply the inverse of R for the left hand side and right hand side to find what is the X. So X will be equals to the inverse of R multiplied with the Q transpose multiplied with the matrix B. Okay, so for the inverse of the R will be equals to the 0.113200, negative 0.2704, 0.1883, 0.2750, negative 0.4704, and 0.3359. After we find the inverse of R, so now we can find the X by substitute the inverse of R, Q transpose, and the matrix B. So multiply all the value inside, so I can find the X will be equal to the 1.5200, negative 1.1081, and 1.0705.
So the input 1 is our question, which is matrix A and also matrix D. Then I will discuss the coding of the orthogonal basis. We let x1 as 2743, then transpose the x1 matrix to become xt1 and continue by xte1, which will pick the first element from the vector. The output is shown in output 3, 4, and also 5. Similar code will be used for x2 and also x3. Then we calculate v1, v2, and v3 by using the formula in terms of coding. We set capital V as our orthogonal basis, and the solution is shown in the pink region.
So I will discuss the coding of the orthonormal basis. Calculate each of the unit vectors by using the formula in terms of code, where we set them as VV1, VV2, and VV3 as shown in the figure. In the end, we transpose them to become the orthonormal basis as capital Q, and the solution is shown in the pink region.
Then This is about the built-in symbol of QR decomposition. As the QR decomposition built-in symbol is being run, we will have two solutions and we set them as QT and the small letter R. We use the built-in symbol of map in input 24 to make a better arrangement of the QR decomposition solution. In the end, we use linear solve to find the solution as shown in the pink region.
Next, this is about the coding of the handwriting method. We find R by multiplying the transpose of capital Q with matrix A. In the end, we use linear solve to find the solution as shown in the pink region.